Alright guys, welcome to 8.1. Excuse the background noise here. I'm in my office and Mrs. Denton's room is rather loud today. Anyway, 8.1 geometric mean. So we're going to figure out what is this thing called the geometric mean, and then we are going to solve problems related. So here we go, the geometric mean. Basically all the geometric mean is you take two numbers and multiply them together and take their square root. So the best way to look at that is through this example. You have this example where you have the numbers 9 and 4. The geometric mean of 9 and 4 is simply take 9 times 4, which we know is 36, and then take the square root. The square root of 36 is 6. The geometric mean of 9 and 4 will be 6. So that's what a geometric mean is. This one's not in your notes, but I wanted to show you an example here before your example. If you found the geometric mean of 8 and 10, that would be the same thing as the square root of 80. Okay, and this is what I want to show you is with radicals, you want to always take out the perfect square. So if you think about what a perfect square is, it's anything multiplied by itself will give you a perfect square. So 1 and 1 is 1, 2 times 2 is 4, 3 times 3 is 9. And if you just keep going here, the pattern continues here. So we have 16, 25, 6 times 6 is 36. 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, right? So there's a bunch of perfect squares. What you want to do is look for something that goes, like, if any of these go into 80 evenly, I'm gonna actually divide it out and take it out. So I know that 4 does. Anytime 4 goes into something evenly, I also want to check 16. I know that 16 does here. But if you didn't, you could check it, right? So do 80 divided by 16 on your calculator, you get 5, right? So you could write this as the square root of 16 times the square root of 5. And the reason you'd want to do that is the square root of 16 simplifies nicely to 4. So 4 root 5 is the same thing as the square root of 80. If you put those both in your calculator, you get the exact same answer. All right, so example 1, we're going to do that here with 5 and 45. So if you have 5 and 45, 5 times 45 equals 225. Take the square root of 225 and you get 15. Okay, so that one just breaks down really nicely. For 1b, you have 12 and 15. 12 times 15 is the same thing as, well, that'd be the same thing as 30 times 6, so that would be 180. Okay, so when you multiply those out, you get 180. Take the square root of 180. Well, I'm thinking of perfect squares that go into 180. I know 9 does, but I also know from experience that 36 goes into there. If you didn't, though, you might want to check a couple more of these. So if I did 36, you get the square root of 36 times the square root of 5. That gives you 180. So the square root of 36 is 6. Square root of 5 is not very well simplified. It goes to some decimal, so we're just going to leave it as root 5. All right, so now let's take what we just learned and apply it, theorem 8.1. Okay, so basically, if you have a right triangle and you draw an altitude down from the vertex of that right triangle to the opposite side, like we have shown here, what happens is you create 3 similar triangles. Okay, because you're gonna have 3 right triangles that are formed. So you'll notice here in the example, if you look to the right, it says if CD is the altitude, this guy right here, to the hypotenuse AB of right triangle ABC, then we know that these 3 statements are true. Okay, so if you compare and they color coordinated there for you so that it makes it easier for you. So the first one says ACD. Okay, so in this case, the D is the right angle, right? So notice that in the black triangle, that D, the right angle would have to relate to the right angle that's there. So D and C, those 2 things have to, those are the 2 similar angles, right? So they have to be in the same order. Same is true if you looked at CBD and ABC and ACD and CBD, right? So just make sure that it's always easy to just make sure that your right angles match up. Okay, so if your right angle shows up as the last vertex that you're labeling on your triangle, make sure it does it in both. Is all I'm saying when you're making your similarity statement. So example 2 says write a similarity statement identifying the 3 similar right triangles in the figure. All right, so we know that it's going to be the small right triangle, the medium-sized right triangle, and the big one. Okay, so I'm going to start by labeling my small right triangle. So to do that here, I'm going to put my right angle as my middle angle. Okay, so I'm going to say triangle MPK is similar to, and then I'm going to go to my medium-sized triangle, which would be LPM. Okay, and that's similar to, on the big triangle, LMK. So notice on all of these that my right angle, is the same in each one. It's always in the middle, right? So it's P on the small guy. On LPM, it's the middle one, and then on LMK, notice that M is the right triangle, so it's always in the middle. So I would encourage you to do something like that just to keep it all straight. Okay, so that's the similarity statement. Let's go to 2B. So for 2B here, let's see what we can do with this one. Again, I'm going to keep my right triangle. I guess I'll keep it in the middle just to keep it consistent. So if you look at our small triangle there, we could say that triangle STR is similar to triangle, on the medium one, that would be QTS, which is similar to, on the big one, QSR. And again, on all of these, the right triangle's the one in the middle. Okay, so keep that straight when you're identifying those. And then it says if triangles from 8.1 are similar, then these are the ratios that are always going to hold up. Okay, so you might want to just memorize these, but basically any part of these, since they're similar, they're gonna be proportional. So the short over the long leg, the hypotenuse over the short leg, or the hypotenuse over the long leg, they're always going to be proportional or equal in value. Okay, so we can use that here shortly after I talk about the geometric mean altitude theorem and the leg theorem. We'll do an example and then we'll be done. So the geometric mean altitude theorem just says that the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. In this case, that would be x and y. The length of this altitude is known as the geometric mean, so this is important. So the length of the altitude here is the geometric mean between the lengths of those two segments. So if you took x times y and took the square root of x and y, it would equal h. Okay, so that's what the example here is showing. That's the geometric mean theorem, altitude theorem. And then we have the geometric mean leg theorem. This says that if the altitude is drawn to the hypotenuse of a right triangle, it separates the hypotenuse into two segments, x and y. The length of the leg in this triangle is the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So in other words, it says here, the example is the best way to understand these. If CD is the altitude to the hypotenuse, AB, in the right triangle, ABC, then C over B. Okay, so C over B is this distance right here, the big distance, the hypotenuse distance. So this is like your hypotenuse over, in the big triangle, over the hypotenuse in the small triangle has to equal the hypotenuse in the small triangle over its opposite leg. Okay, so notice it would be easier if I said hypotenuse, you're basically just using this idea right here. The hypotenuse over short has to equal hypotenuse over short, depending on which triangles you're looking at, right? So B is the hypotenuse of the small triangle, but it's also just the leg of the big triangle. So it depends on what perspective you're looking at, okay? So again, if that's the case, then you can see that B is equal to the geometric mean of x and c. This one's not as important because you can solve this using other methods, but this one is definitely one that's used a lot, the geometric altitude theorem. All right, so example 3, for 3a here, we see that we have three variables that we're trying to solve for. Okay, so the first one that I would solve is this guy, because I know that that's equal to the geometric mean of 8 and 25. So I can take the square root of 8 times 25. By the way, I could simplify that first, but let me not confuse you here. 8 times 25 is equal to the square root of 200. But I know there's a 25 in there because I just did that, right? And I know there's a 4 in there. So really, 25 times 4 is 100. There's 100 in here, which is a perfect square. So I can rewrite this as the square root of 100 times the square root of 2. Okay, so for the z value there, that's the same thing as 10 root 2. Okay, so z is equal to 10 root 2. We just solved for that one. Okay, now, you don't need to use your other theorem, because now that you have that, you can simply use the Pythagorean theorem to solve. So for this triangle here, if you were trying to solve this for x, you could just say 8 squared plus 10 root 2 squared is equal to x squared, and solve it out. And then on the big triangle, you could say 10 root 2 squared plus 25 squared is equal to y squared to get your y value. Okay, so you can just use the Pythagorean theorem. By the way, when you do that, your x value should come out to 2 root 66, and your, so careful with that one. That one's hard to find, the 4 that's in there, but make sure you try that out. And then your y value here would be 5 root 33. So hopefully you're able to get those. For 3b, kind of the same deal here. We can say that the square root of 9 times x is equal to 12. So to get x by itself, you could square both sides. You could say 9x is equal to 144, right, which is 12 squared. Divide both sides by 9 here, and we get that x is equal to 16. Okay, so once you have that, you know the hypotenuse of this guy, right? This is a right triangle, by the way. So that would be 25. But you don't know either of the legs, so you might want to solve for z, right? So I can do 9 squared plus 12 squared equals z squared. Solve this for z. When I do, I get 15. Once I know that that's 15, I can solve for the big one, say y squared plus 15 squared equals 25 squared. And when you do that out, you should get y is equal to 20. All right, guys, that's it for now. Let me know if you have any questions. We will be doing the odds 1 through 25, and I'll have a homework sheet for you guys. We'll see you guys next time.